Hi, hello. Okay, so we have been working through the definition of homomorphism, and I want to make a couple comments about where we are. So most folks who take this course don't really struggle too much with the solving of linear systems. Seems very concrete to them. You follow these steps, you always get the right answer. That seems very sensible. The next step up in abstraction, not very abstract. The next step up in abstraction is to study collections of linear combinations. And most folks, when you study vector spaces, are pretty good with that. Okay, so vector spaces have these rules. You always follow these rules. They arise naturally somehow from linear systems. It all makes a lot of sense. Or at least it makes pretty good sense. Next up, though, you start studying connections between vector spaces. So isomorphisms, which is pretty natural because when you study vector spaces, you start saying to yourself, this space is just like that space. So that's called an isomorphism. But then you get to homomorphism, and my experience in teaching the class is that that's kind of the point where you have built up this pile of stuff, and it's starting to seem a little shaky, just a little shaky. So that's the point. That's exactly the moment when a person needs to say, let's stop. We'll make this concrete by doing lots of numerical examples. 3's and 2's and 5's help to make x's and y's make sense. We'll look at it this way, we'll look at it that way. So that's the whole idea of what we're doing now. We're not racing ahead, we're stopping, because this is the point at which very often a person taking this class starts to feel like, I was getting it good in the first chapter, and now the second chapter, okay, but this third chapter, it's starting to feel a little fuzzy to me. So when things start to feel fuzzy, you say stop, take a breath, let's make it concrete and do lots of examples, look at it different ways. So far we have looked at it one way, the definition of homomorphism, and sort of chugging through, can we prove that something is a homomorphism, can we verify this thing, that thing. You get a feel for what homomorphisms look like. Second thing we did was to worry about the sort of how homomorphisms act. They organize the domain into inverse images of elements from the range. So the example that I talked about a number of times so far is you look at the homomorphism that is projection from R3 to R2. You stand at a point in R2, I've been thinking of 5, 6, I think, and you ask yourself which vectors project to me. You look up, you look down, all the vectors above and below you, that entire line of vectors, all the vectors above and below you collapse down to be you. I called those, say, the red vectors. And then the definition of homomorphism, the preserves addition part of the definition of homomorphism, is that you can understand that a red vector plus a blue vector makes a magenta vector. That is to say, these inverse images of points from the range, these ways that the homomorphism organizes the domain, have a structure to them. They add according to the rules that the definition of homomorphism gives you. Okay, and we saw a number of examples, and you know, work through some. Do it in this case. Do it in this case. Do it in this case, so a person gets some feel for how exactly it works. Today we'll see yet another example of trying to understand what homomorphisms are. So we are going to draw some pictures. We'll look at some homomorphisms and say, here's some pictures. To draw some pictures, the obvious thing to do is to work with real spaces, the plane in this case, because I can draw plane pictures better. And so I'm going to have some homomorphisms of what do they do in the plane. Okay, so last time we did the sort of algebraic expression of this homomorphism divides the domain up into inverse images of points in the range. The way algebraic way to state that is to say the nullity plus the rank equals the dimension of the domain. That if you're looking at the homomorphism of projection and you're standing in the plane at 5, 6. There's an entire dimension's worth, a line of points above and below you. That's a one-dimensional set. That entire dimension collapses. So the three-dimensional domain and the two-dimensional range, where'd the one dimension go? And the answer is, for every point in the range, an entire dimension's worth of points collapses to become that point. Rank plus nullity equals the dimension of the domain. So of course the check-in has some examples of that, and here we go. So two different homomorphisms, and as usual, I'm not going to verify that they're homomorphisms. We're kind of past that now, and I'm looking to find the null space and the range space for each. Okay, let's see how I do here. Organize my desk. There we go. Okay. So I'm looking first at let's see, how's it go? It's ABC maps under G to the quadratic polynomial 0 plus a plus 2c x plus 0x squared. I could have just written a plus 2cx. I wrote the 0x squared and the 0 just to try to emphasize that this is a quadratic polynomial. It happens to have a constant term of 0 and a coefficient of x squared of 0, but anyway, it's a quadratic polynomial. And I'm asking myself, what is the null space? And in a minute, I'll ask myself, what is the range space? So we've done lots of these, but you can always do more. It really helps to make something concrete, to do sort of overlearning. Do enough examples that you start saying to yourself, yeah, they all go the same way. I'm tired of this already. That's a good feeling. When you're tired of it already, it means there are no surprises left. Anyway, enough blabbing on my part. So we're looking at the set of ABCs where a plus 2c is 0. And so I'm looking at here, this is the set of, in place of a, I'll write a minus 2c. Oh, that's right, where b and c are free. And so I'll parameterize that as I always do by breaking out the b and the c. And 0, 1, 0, b, and minus 2, 0, 1 by c. Again, b and c are free. Okay, and obviously the basis here is, I'm not going to verify that it's a basis. I'm not going to check linear independence or any of that stuff. But 0, 1, 0 and minus 2, 0, 1. It's a basis. So because there are two things in the basis, the nullity is 2. Okay, so we have a good sense of what the null space is. It's a plane. Inside of R3, it's a plane. These two vectors whose bodies lie in the plane, not just the tip, the entire body lies in the plane. These two vectors form a basis for that plane. What about the range space? Oh, range space of G. Sorry, I forgot to write the G. Now, because the nullity is 2, and the dimension of the domain is 3, so we have that the rank of the map must be, 2, 3, I mean, it's a 1. So what that tells you is that the range space is just all multiples of x. That's right. It's a one-dimensional space. It can't be just like the even numbers multiplied by x, or that doesn't make any sense. You have to be able to multiply by any scalar, so it's all numbers multiplied by x. And obviously a basis for the range space would be, a basis here would be just singleton x. The sequence consisting only of an x. Okay? I'm kind of out of space on this paper, so let's have a whack of it at a new paper for the next map. All right, and the next map happens to be from R to R3, and I called it H just to give it a different name, and it takes a number from the real line to A, 3A, 0. Okay, and same two questions: the nullity, the null space, and the range space. Okay, so the null space is obviously it's the set of members of the domain with the property that A equals 0 and 3A equals 0. I know the second equation is redundant on the first, but anyway, I wrote it. And of course, that's exactly the set that contains only the number 0. So this is the trivial subspace of the domain. Trivial subspace of the domain. Okay, you might remember it's a little bit obscure, but I'm reminding you. So you might remember because I'm telling you that the basis for the trivial subspace is the empty sequence, and that the nullity, what makes the arithmetic work out, the nullity is 0 because there are 0 many things in that basis. And here I go now. I'm working on the range space. So because the nullity is 0, oh, it's h, oops, h equals 0, then the dimension of the domain is 1. So what I meant by the arithmetic working out is that within the rank of the map must be 1. And in fact, the range space of H is obviously the set of points that lie in the xy plane, because there's a 0 there, and lie on the line, in the xy plane, lie on the line y equals 3x. So that's the line y equals 3x in the xy plane. Okay? So once, as with the first example, the fact that we found the nullity enabled me to find the rank, and so I was, it's clear that the range is a subspace, but the range has to be all of, or else it wouldn't have the right rank. Okay, very good. Oops, put the cap on my pen so it doesn't run out. Okay, very good. Okay, so what I want to talk about today then is what I began discussing. We want to look at homomorphisms. Homomorphisms are the point in this course where people start saying, I thought I was getting this and now I'm not so sure. So we want to look at homomorphisms in a couple of different ways and do lots of examples. Examples means numbers. If things are getting too abstract, then try it with numbers. Still too abstract, try it with more numbers. Do another 5. Kind of stuff, and that's how it becomes concrete, until at some point you're saying to yourself, oh, these all go the same way, and you go back and look at the theorem, and darn it isn't if that isn't exactly what the theorem says. So we're in that stage, we're in the middle of that process, and we're trying to build up the habit of doing that. Okay, so here we go. I'm trying to understand what linear maps are by understanding how they act in the plane. Just a third way to look at homomorphisms, at linear maps, is I'm fixing some place I can draw, namely the plane, and I'm going to draw some. All right, so in real n space, a line through the origin is the set of all multiples of some vector. So if you fix a transformation from real n space to real n space, remember I personally try to limit the word transformation to where the input and output spaces are the same, but that's not universal. Not everybody does that. I try to stick to that, but other people do something different. But here we go. That's a transformation from Rn to Rn, and it's a linear map. It's a homomorphism. So its action has to be that R times V maps to, under T, maps to R times T of V. So the members of this line map to the members of this line. R times V maps to R times T of V. Here I called it S instead of R, but it's the same thing. Multiples of V become multiples of T of V. That's a line. So this paragraph says that under a transformation from Rn to Rn, lines through the origin map to lines through the origin. That's simply a restatement of the rule, the second rule for the definition of linear map. Lines through the origin map to lines through the origin. So the action of T is determined by its effect on any non-zero element of the domain line. If you tell me where V goes to such and such, whatever T of V is, then I know where everybody in the line goes. 3 times V goes to 3 times T of V. 5 times V goes to 5 times T of V. So all you got to do is tell me where V goes, and I know where everybody goes. Okay. So how does that help here? So let's look at the line y equals 2x, sort of canonical line in the plane. and pick a transformation. And I'm not a very imaginative person, so when I have to pick a transformation, I pick 1, 2, 3, 4. So the map effect on any vector in the line is easy to compute. Where does 1, 2 go? It goes to 7, 10 because I plugged in 1 and 2. And then the linear map property that T of R times V is R times T of V imposes a uniformity on what T does. What is T going to do to twice V? It's going to do twice the thing. It's going to have twice the effect. What is T going to do to minus 1 times V? It's going to have minus 1 times the effect. What is T going to do to 100 times V? It's going to have 100 times the effect. So 2, 4, minus 3, minus 6, R2R, they all show the exact action of T. 2, 4 is double the 7, 10. Minus 3, minus 6 is minus 3 times the 7, 10. And R2R is R times the 7, 10. In short, here, summarizing, the action of T on any non-zero vector in the line determines its action on any other vector in the line. Did you see the notation's a little tight there? So that's the span of the set containing the one vector V. You know, that's the line. Multiples of V. Okay, so again, I talked about how lines map to lines, and you can figure out where any point in the line goes by knowing where the one point in the line goes. So how does that help me picture homomorphisms? And the answer is that every plane vector, except for the origin, is a non-zero member of some line through the origin. So to understand what a map from the plane to the plane does to plane elements, it suffices to understand what it does to lines through the origin. If I want to know what T does to an arbitrary element of the plane, well, that arbitrary element of the plane is on a line through the origin. So if I understand what T does to every line through the origin, I understand what T does to everything in the plane. By the prior slide, to understand what T does on a line through the origin, fix the line y equals 2x. To understand what T does on a line through the origin, it suffices to understand what it does to one non-zero member of that line. If you know what T does to 1, 2, then you know what T does to every vector in the line y equals 2x. Okay? So all I got to do is pick one point from each line through the origin, figure out what T does to that one point, and I'll know what T does to every point in the plane. Again, I'll pick one point on each line through the origin. For example, in the line y equals 2x, I pick the point, for example, 1, 2. If I know what T does to 1, 2, then I know what T does to every point on that line through the origin. So I'm called upon to pick one point on each line through the origin. I'll pick the point that is a distance 1 away from the origin, because so 1. And we know how to draw the points that are 1 away from the origin. It is the point whose x-coordinate is cosine and y-coordinate is sine, for where T is the angle. You see that these are colored, and I'll talk about what the colors mean in soon enough, but have to do one thing at a time. You might notice, it's a little bit subtle, but you might notice down here that this point at 180 degrees, this point at pi radians, is not actually included because I included the point at 0 degrees or radians, and I only want one point from the line through the origin, so that's why that's an open circle. Anyway, it's a very fine point, that doesn't matter. So I'm going to start looking at some linear maps. This is the first linear map I looked at because it's the easiest linear map I could think of. Easiest, not trivial. Linear map I could think of. You double the x and you leave the y's the same. What does it do to every point in the plane? Well, we pick one point from each line through the origin and see what it does to that, and it's very straightforward. What does it do, for example, to the point 1, 0? Why, it sends it to 2, 0. What does it do to the point 0, 1? Why, it sends it to 0, 1. What does it do to intermediate points? They go to intermediate places. So this semicircle maps to this upper half of the ellipse. This semicircle maps to this upper half of the ellipse. Well, what happens if you multiply x instead of by 2 if you multiply by a negative, like -2 or -5? So I did -1 just to an illustration. And so it's a little trickier to see here. Do you see that this goes red, oops, I went the wrong place. Sorry. This goes red, orange, yellow, green, blue, indigo, violet kind of stuff. So this is Roy G. Biv. So it starts with red on the right-hand side and moving counterclockwise, moves through blue and violet. When you multiply by -1, now red is on the left-hand side and it moves like so. So that is to say that the action of multiplying by -x changes this from, changes the orientation by which you traverse this circle from counterclockwise to clockwise. Changes the orientation under which we are traversing this circle as t, the parameter, the angle, goes from 0 to pi. First we were counterclockwise, now we're clockwise. So we're starting to get some small picture, we'll see many more examples, but some small picture. Transformations of the plane are going to change this semicircle to different shapes, ellipses, to different shapes. And another thing they can do is change the direction under which you traverse the circle. That's why I needed the colors. Next example. Before I changed the x in my two examples so far. Here I'm going to change the y. So x goes to -x is held the same from the previous picture, but now y goes to 3y, and a person can see I had to change the scale of the picture to make it fit in good. You can see what happens is that instead of being 1 tall, I'm now 3 tall. So I'm still, again, it's a little hard to read, but I still, again, the -x causes the semicircle was traversed counterclockwise, and over here the semicircle was traversed clockwise. If you go Roy G. Biv, it's clockwise. But the difference is, although it's still at +1 and -1 on the x-axis, now it goes up to +3 on the y-axis, so it stretches, dilates, it elongates the picture by a factor of 3. The two dilations combine independently, and the first coordinate of the output uses only x, and the second coordinate of the output uses only y. So what happens, for example, if I mix some x's and y's in the first component, some x's and y's in the second component? So, here I go. I'm mixing some x's and y's. So y goes to y, just to hold that, so that's not a factor. X goes to x plus 2y. So again, with the semicircle over here, what happens to points on lines through the origin? Well, over here you can see. What the heck? This is skewed. So what's happening here? I'm asking a person to think of this picture. Imagine that you had, say, a deck of cards. Oops, there we go, a deck of cards, and you push it, but you don't push the whole deck. Instead, you lean on it so that it starts to go like this. So the top slides more than the bottom. The bottom doesn't slide at all. I'm trying to get flat. Not so good with the camera. The bottom doesn't slide at all, but because you leaned on the top slides quite a lot. That's called a shear. So what's happening here is that for those points in the plane, those xy's where y is 0, this map sends xy to xy, because the 2y has no effect. For those points in the plane where y is 1, this map adds a 2 to the x-coordinates. See, there it is, 2 to the x-coordinates. So the effect of this map, this is a perfectly good linear map, perfectly good linear transformation. The effect of this map is to change the x-coordinate depending on the starting y-coordinate. With a high y-coordinate, you'll see a big change in the x-coordinate. With a low y-coordinate, meaning 0, you'll see no change at all in the x-coordinate. So this is a skew. And again, it's like you had a rickety table, and you leaned on the table. And so what's happening then in that case is that the top of the table is moving a lot. The part of the table, the part that's stuck to the ground, is not moving at all. So this is called a skew. And linear transformations can do that. Here is a skew in the y direction. So I'm gonna mix the x's and y's in this way. Leave the x alone, mix the x's and y's in this way, and you see the same effect here. You see that something interesting is happening here. Is that what's happening here is that when we change the when we put x's down here, if x is not 0, and indeed x is not 0, whoops, I'm sorry, pointing in the wrong place, and indeed x is not 0 here. If x is not 0, then there's a pronounced effect. So if x is not 0, then you see that the point moves. The red point moves. So does the violet point. On the other hand, if x is 0, if x is 0 right here, you see no effect at all. So the green maps to the green. Standing back from it, understanding it as a skew, but standing back from it, what you see is a rotation. I am no longer projecting, I'm no longer looking like, there we go, no longer looking like a sort of flat ellipse. Instead, I'm looking like an ellipse, there we go, looking like an ellipse that has rotated. So there's some action of rotation here to move the ellipse that we saw earlier, so that its long axis is no longer on the x-axis. Its long axis is now somehow pointing off here in an arbitrary line, in some kind of line. Hard to see how it's arbitrary. It's of course determined mathematically. So I went from 2x to 1/2 x, just playing with the numbers because that's how you make things concrete. And with 1/2 x, you see instead of being 2x, you go to 1/2 x, so you see sort of a quarter of the effect. Again, points that have an x value are affected. Points that have an x value are affected. Points that have a 0 for an x value are not affected. Points that have a 0 for an x value, the green points, are not affected. They are unchanged. But changed are the points that have x equals 1 or x equals minus 1. Of course, x equals 1/2 is also changed, but it's not changed by as much. I'm going to observe something that's a little hard to see here. Restating what I just said a minute ago, is that a red vector gets moved a lot, a green vector gets moved not at all. So we are affecting points in this curve, they're not affected uniformly. Okay, so some points it's not like we picked up this half circle and somehow moved it uniformly. That's not right. Some points on the half circle are remaining the same. Some points on the half circle are moving. Another example of an action that we've seen for linear maps that we talked about, for example, when we did bases, is rotation. So here I did rotation. This is plain, simple rotation. Everybody rotates. You pick up the entire half circle and rotate everybody by whatever degrees, whatever angle theta is. No change of orientation here. This goes red, orange, yellow, green, blue, indigo, violet, counterclockwise. Red, orange, yellow, green, blue, indigo, violet, counterclockwise. So it's very uniform. We've seen, of course, with linear transformations, we just were talking about a few minutes ago, projection from R3 to R2. Well, here I don't have R3, so I'm projected to R1, and it just, it just squeezes down here, and there you go. You can hardly see it. It's on the x-axis, so it's basically gone. You can kind of see the colors a little bit. Now, the map doesn't have to squeeze down to the x-axis. You can make it squeeze down to the line, for example, y equals 2x. So there we go. I've projected to the line y equals 2x. So some points project up, some points project down, but they all project to the line y equals 2x. And again, I'm not a very imaginative person, so when I go to make up an arbitrary map, I made up 1, 2, 3, 4, I don't know. So I typed 1, 2, 3, 4 into my computer drawing program, and from 1, 2, 3, 4, this tells me what is the action of the map on every point in the plane. So red goes to red, blue, green, indigo, violet, etc. And again, you see that your output is half of an ellipse. And again, you see that there's been some rotation, so that the long axis, the major axis it's called, of the ellipse is not on the x-axis or the y-axis. Instead, the major axis of the ellipse is somehow at some angle. And it's a little subtle, but you might notice because your sort of antennae have been raised to this point, you see that this goes red, orange, yellow. This is a counterclockwise. You traverse counterclockwise when you go from red to violet, and here you're going clockwise when you go to red, from red to violet. So here you're seeing that the orientation has been reversed. It's a little subtle, but that's why I have the colors. So not only do you see dilation, that you see stretching, you see some kind of rotation, but you'll also see orientation reversal. So 1, 2, 3, 4 is actually a pretty good example. Okay, so again, what is happening here is that we are trying to find different ways to look at homomorphisms. What is it that homomorphisms can do, and get some picture in our mind, some sort of framework or schema on which we can hang new homomorphism thoughts. So homomorphisms can do some things and they can't do other things. What kinds of things can homomorphisms do? And we've seen it's an exhaustive list, but you have no way of knowing that it's an exhaustive list. But we've seen the pictures of what a homomorphism can do in the plane. Basically, these I listed, dilation, rotation, orientation, reversal, all things that homomorphisms can do, for example. Okay, so that today's material was in some sense a little bit extra, that's outside of kind of the main stretch, and now next time we're going to go back to talking sort of back in the main flow of things, and we will try to find a computational scheme for representing homomorphisms, a way to compute homomorphisms that's convenient, and that computational scheme will involve matrices, and at that point we'll sort of really know what matrices are doing. Okay, very good.